Welcome to the second video in our video series on chemical reactions. Now, in our first video we learned that chemical reactions are processes where new substances are formed, which we call products. Most chemical reactions can be broken up into three fundamental or basic steps. Step 1, the reactant molecules bonds are broken. Now, the reactants are the substances that one starts off with before the chemical reaction or the chemical change takes place. In this process, energy is taken in to the system in order to break the bonds of the molecules. Then in step 2, there is the formation of a highly unstable activated complex, which is basically all the atoms that form the reactant molecules that have now been separated from each other and are next to each other. It doesn't last very long because this is a very unstable arrangement. Then in step 3, new bonds are formed as energy is given out to the environment, and these new bonds form part of what we call the products, which are the final substances that remain after the chemical reaction has taken place. So if we consider this example where hydrogen gas reacts with iodine gas, and these particles are placed in what we would call a reaction vessel, and these particles are able to collide with each other, and if they collide in the right way with the right amount of energy, in other words, they hit each other hard enough, they will break apart, as we see here, and will reform into a product, into molecules that look very different. So for instance, the hydrogen and the iodine, this would be the hydrogen molecule, this would be an iodine molecule. There would obviously be millions and millions and millions of these different type molecules colliding with each other. But for the sake of simplicity, we only represent one molecule of iodine and one molecule of hydrogen colliding with each other and forming an activated complex in order then to produce two molecules of the product, which would be hydrogen iodide. Now note that the original molecules, and I refer to this as the hydrogen molecule because the hydrogen atom is smaller than the iodine atom. So this is a smaller molecule than this. So this would be the hydrogen molecule. This is the iodine molecule. Look very, very different to the final molecules, the product molecules, which each consist of one hydrogen atom and one iodine atom. So this is a hydrogen iodide molecule. So we can see that this is very clearly a chemical reaction because the actual structure of the molecules has changed. It's not that the distance between the molecules has changed only, it's the fact that the actual structure of the molecules has changed that makes this a chemical reaction or a chemical change. Now, when considering the energy changes within a chemical reaction, we can think of it as if the reactants would need to be moved over an energy hill. So if we look at the reactants as if they were a big boulder and that they would need to be moved over a energy hill in order to become products, then the minimum energy required to react would be the height of this energy hill. The activation energy, as we refer to it, can be represented by the symbols EA, capital E for energy, little a for activation. And so in order to activate the reaction, in order to break the reactant molecules apart, one would require a minimum energy, which would then take the reactants in a broken form up to the hill, and that would be the activated complex. A boulder would not stay on top of the hill for very long because it would be unstable, and then moves down here, and in so doing becomes the products. Now, one needs to be careful when one makes use of illustrations or symbols like this, because we can see that the boulder is the same here and here, but in a chemical change, the actual structure of the reactants is different to the structure of the product. So the main reason why we use this illustration is for you to get the idea that it doesn't happen easily in most cases in chemical reactions for the reactants just to become the products. There is a certain amount of energy that is required for the reactants to then change into products. So EA, the activation energy, is the energy required to break the bonds of the reactants molecules. And depending upon the type of reaction, on the type of reactants, that will determine how big or how small the activation energy is. So now, looking at the energy yield diagram in more detail, we refer to the official name of these types of graphs or diagrams as the energy pathway diagram or the energy profile or energy profile diagram. It consists of a vertical axis, which is the potential energy of the substances that we are looking at in the reaction. The horizontal axis is the progress of the reaction, or the time from the start. We start off with the reactants, and on the vertical axis, the value at this point would be the energy of the reactants, which we represent as ER, R for reactants. The height of the energy hill we refer to as EA. That's the energy taken into the system to take the reactant particles from ER up to the top here, which is a higher energy. And that's the energy of the activated complex. And the higher the energy of the particles, the more unstable they are. So this is the most unstable point in the energy pathway of the reactants through to becoming products. Then there's energy that is given out, and the final energy of the substances, that is the energy of the products, which we represent as EP. And so the difference in the energy given out when the new substances are formed compared to the energy taken in is known as the enthalpy change of the reaction, or the net energy of the reaction, or the heat of reaction. And when we do calculations in the next video, in this video series, we will be working this value out for specific reactions. So looking at this energy profile in more detail, we see that for hydrogen and iodine reacting to produce hydrogen iodide, that firstly, the energy given out is greater than the energy taken in. So what that means is more energy is given out than taken in, and therefore we call this an exothermic reaction. This means that energy is given out from the actual particles, the molecules of the substances in the reaction, to the environment. And that is because the final products have got less energy than the initial reactants. So there's a law in physics and chemistry called the law of conservation of energy, which states that energy cannot be created or destroyed, but is transferred from one form to another form. Now, if the final products have got less energy than the original reactants, it means that the final products are more stable than the initial reactants. Now, where does that difference in energy go to? Well, if the energy of the product which is in the chemical system is lower than the chemical potential energy in the reactants initially, it means the difference must have been transferred outside of the system of the particles to the environment. And the word exo means exit, to go outside, external. And so that net energy there is now found in the environment, and that is either observed as an increase in temperature, or that the energy is observed in the form of light. Let's now consider an example of an exothermic reaction by looking at this YouTube clip.
Today we're doing a reaction between potassium permanganate, very unstable, and glycerol, not as stable as it could be. And that's going to be an exothermic reaction producing heat. First, I got to grind this stuff up because it's very coarse. It's kind of purple. And it's very pretty. It's kind of the color of grape juice. And I'm going to grind it. So one time a student told me that they couldn't come to class to take their test, and I was like, why? And they said that a cat caught on fire, and I was like, well, you should have known, like, that, you know, cat and starting heat plus oxygen equals flaming cat. But I said, okay, you know, go take it to the animal hospital, and I'll get your test to you some other day. The moral of the story is you should never burn candles around a cat. So you can kind of see it's getting very fine, and we're ready to add some glycerol to this. And I'm wearing my safety glasses. Always practice safe science. Okay. Really don't want to spill it, because if you touch it, it'll turn you brown for a week where you touched it. So I'm going to make a little indentation, and I'm going to pour some glycerol. Glycerol is a really sticky liquid. It's actually the backbone of your fat molecules. Okay, here comes, it's about go time. And now I'm going to get out of the way.
So note from the video that other than the fact that scientists are generally quite weird, that the original reactants were initially kept separate, and the potassium permanganate and the glycerol, when they were put together, released a large amount of energy which we could observe in the form of light and heat. So this is an exothermic reaction, and once this reaction has taken place, the product that is left over, which would be a powder on that tile, would actually be very, very stable. If you tried to react that with something else, you would find it would be very, very difficult to do so. And the reason for that is because the product's molecules would have a very, very, very low energy. So please don't think of the energy, the light energy and the heat energy, as a product. When we talk about product in the context of chemical reactions, we are referring to the substances that are left over at the end of the chemical reaction. And so energy isn't a substance. So this is an example of a highly exothermic reaction, and it is also an example of a spontaneous reaction. He did not need to put extra energy in the form of lighting a match or putting in an electrical spark. As soon as the glycerol and the other reactant, which was the potassium permanganate, As soon as they came into contact with each other, they were able to react and produce the product and the amount of energy that we saw in the form of light and heat energy. So this is a spontaneous exothermic reaction. There is another class of reaction referred to as endothermic reactions, and endothermic reactions have the characteristic where the energy that is given out in forming the new bonds for the molecules of the products is less than the energy taken in. This results in the fact that the energy of the products is actually greater than the energy of the reactants. And the word endo means internal, taken inside. So the internal energy of the products, or the potential energy of the products, is higher than the internal energy of the reactants. And because of the law of conservation of energy, it means that this higher energy, that energy must have come from somewhere outside of the system of particles. And so therefore the environment loses energy, and this is often observed as a drop in the temperature of the environment surrounding the chemical system made up of the reactant and the product molecules. Let's consider an example of an endothermic reaction.
In this video, I'm going to show you an endothermic reaction between ammonium chloride and barium hydroxide. So I've got my thermometer in here so we can keep track of the temperature. It's currently reading about 18 degrees in the lab. And I love this experiment because this is basically what we call bucket chemistry. You just chuck a load of stuff in a beaker. Right, barium hydroxide in there. Nice. And then I need to get some ammonium chloride in there. And we can see that these two are at the moment both in quite the white powders. Not very interesting white powders. Quite a lot of stuff comes as a white powder, and this is starting to absolutely stink. Ammonia pongs basically. So I'm just going to mix this up. It's quite hard to mix at first because I'm trying to mix two powders together, one of which is quite lumpy and the other one which is quite fine. So I don't really want to mix up. Use my thermometer. Okay, this is really starting to pong quite strongly of ammonia now. Mixing things up, and if I feel it, it still feels room temperature. It feels room temperature. It doesn't really feel cold or anything. It just feels normal. And you can see this is really smelly. And you can see these two are starting to come together now, and it's a bit hard for you to see in there, but they're not powdery. It's kind of like a bit of a mush at the moment. And if the temperature has already dropped to, if I can just bring that closer and try and show you, the temperature's already gone below -10 on this. So I'll take the thermometer out so I don't break the thermometer now, and go back to using a spatula. So this is quite hard to stir, but it's actually turning into a liquid form. There we go. It's gone completely liquid. Now the two of them are mixed, and if I show you that, you can actually see it's liquid and it's going to start to pour. And just to prove to you that it is actually cold, I've got a wooden block here and I've got some water, so I'm just going to pop a drop of water under there, put the mixture back on, and then hopefully I should be able to lift up, not quite yet, I should be able to lift up the beaker, lift up a bit of wood using a bit more water on there maybe to help it out. Give it a bit of a stir again. So this reaction actually drops down to about -30, and it's really hard for me to touch here because it really does feel very, very cold. And ta-da! I'm able to lift up the block of wood using the beaker because the reaction's got so cold it's frozen the wood to the beaker. And that is an endothermic reaction. It's taking energy in from its surroundings.
So in this reaction we see that the initial reactants, which were barium hydroxide and ammonium chloride, produced different products, one of them being ammonia in the form of a gas which we couldn't see but which was making the lady very uncomfortable. You could hear her actually trying to clear her throat because it's a very pungent, very strong smelling gas. And in order to do that, it was stealing energy from the environment which we couldn't physically see, in order to produce products of a higher energy than the original reactants. And one of the ways we could see that it was stealing energy from the environment was by using a thermometer. And we saw that the thermometer dropped to about -10 degrees Celsius. And because it did this, she was able to demonstrate that it actually froze the water between the beaker and the wooden block so that she could lift the beaker and the wooden block simultaneously. So this is an example of an endothermic reaction. Now most reactions are exothermic, but there are a small class of reactions which are endothermic, and a little later on in this video series we will look at some other endothermic reactions. Scientists love to classify things, so we have classified chemical reactions that give energy to the environment as exothermic, and chemical reactions that steal energy from the environment as endothermic. But there's another way we can classify chemical reactions as spontaneous, where they happen with very little energy input to start them off with. So in other words, there's enough energy in the environment, what we refer to as the ambient energy, it's the energy that exists there, that it can actually cause the reaction to occur without any external energy input. And then there are non-spontaneous reactions which require a large input of energy to start them off. And this extra energy cannot be acquired from the environment, but there needs to be an input of more energy from another source in order for these reactions to occur. But we'll learn a little bit more about this in the videos that follow. But to end off this video, I would like to set a challenge to you. Can you classify the type of reactions that are found in this video? Pause the video and think about the answer to the question. Well, quite clearly there was a large amount of energy given out to the environment in the form of light energy and heat energy. So these explosive reactions are definitely exothermic. But are they spontaneous or non-spontaneous? Well, how were the crackers exploded? Did they just explode of their own? Obviously not. There was a spark that was needed, or there was a little flame that needed to be ignited in order for the cracker to actually explode. So albeit that this was, or should I say these reactions were exothermic, these reactions were not spontaneous, but non-spontaneous. In the next video, we are going to look at how to carry out calculations using the energy profile diagrams.